Hello everyone, welcome back. So this week's lecture is going to be about uncertainty. So in the past few lectures, we've looked into different types of neural networks that perform different types of tasks, all the way from segmentation, regression, unsupervised learning, and things like this. But there's always a key assumption that we make, which is we have the truth. We have the ground truth output label map or image that we want to predict or regress. And that truth sometimes doesn't actually exist. So when it doesn't exist, we need to start thinking about things like uncertainty. So the lack of existence of a truth and the lack of a way to convey when a network doesn't know what it's supposed to do currently does not exist in everything that we've seen so far. And this is what today's lecture is going to be about. So in this lecture, we're going to do an introduction to uncertainty. Why is it needed? We're going to be looking into Gaussian processes, Bayes backpropagation, and MC dropout as different ways to achieve some degree of uncertainty knowledge. So why do we actually care about uncertainty? In most computer vision, the problems that we have are problems that most humans can create, if not perfect, very good labels for. For example, if I was to show you these two images, there's very, very few people that would misrepresent, for example, the image on the left as being a dog and the image on the right as being a cat, right? This is a task that all humans can do if they're paying attention, obviously. And so the label is very, very close to a ground truth. An algorithm needs to decide if this is a cat or if this is a dog, and it can do so with a very, very high degree of certainty because the human label itself is a very good quality. However, if an algorithm is trained to predict if something is a cat or if something is a dog, what happens if we show an image that is neither of those? An example of this is an image, for example, like this, where I'm showing this little platypus here. So if you were to show this image to a network that has only seen cats and dogs, where the full world that that network has observed only contains cats and dogs, the network will need to make a prediction, either cat or a dog, because this is a two-class problem. We are not allowing any third class, which is other. That's one way of doing it. And also, we're not allowing the network to convey any degree of uncertainty about what it has learned. So the network is going to output two logits, which are going to go through a softmax, for example. And because you'll end up with two probabilities, they're going to sum up to 1. So you're going to have probability of cat and probability of dog both summing up to 1, when clearly this is neither one or the other. Obviously, this problem is significantly exacerbated in the medical setting. Why is that so? First of all, the diagnostic of a patient, for example, if what we're trying to do is to diagnose a patient and the condition that they have, diagnoses are not perfect. What I'm trying to say with this is that obviously every patient has a certain disease and a certain etiology that is causing the symptoms that they're observing. But that does not mean that a disease is diagnosable. And also, it does not mean that if a clinician has diagnosed someone, that diagnosis is even correct. The rate of misdiagnosis in first world countries is actually surprisingly high. It's probably around between 5 and 7% in a standard hospital setting. And for example, in my area of research in neurology, it tends to be actually much higher than that. And that's because diseases are categorical representations of a series of symptoms, of a series of effects, and it is often very hard to categorize on these. It's also very common that patients have multiple pathologies, and these multiple pathologies might interact with each other. So a patient, for example, might be diagnosed as having a pathology and not another, but in reality they have both. It's just that one pathology might obscure the other one, or might, for example, hide some of the symptoms. So the comprehensiveness and the correctness of medical diagnosis is often wrong. And because it's often wrong, algorithms receive those labels which are not perfect. So it's incredibly rare that in the medical setting, our disease codes, our definitions of which pathologies the patients have, are actually ground truths. What they tend to be is what is called a clinical gold standard. They follow the best acceptable clinical gold standard to obtain their diagnosis. And normally when we see a clinical gold standard, we think that is actually quite good. But again, in many pathologies and in many areas of care, the clinical gold standard can actually be quite poor, often also referred as a bronze standard or any other kind of name, which tends to carry some sort of pejorative term, because in reality the quality of the labels is often quite poor. So that's one side, the labels are poor, but more than that, sometimes the labels are poor, but the clinicians know about it. For example, if you were to ask a clinician, how certain are you of the diagnosis that you've given to the patients? In certain settings, they would know how certain they are. They would say, yeah, I'm pretty sure this patient has this because of X, Y, and Z. While in the other situation, they need to diagnose the patient with some disease so that they can then action it. They can start treating that condition. And that actionability actually can cause some other issues, because if you are uncertain, you might be giving a patient a drug that is not really appropriate for that kind of pathology. So if you have all of these things in mind, you have to take into account that there's two bits or 2 points of the equation. There is situations where the labels are wrong, when we're learning from dirty data and the data itself is uncertain due to natural variability of the pathology. And on the other side, you have the problem of actual uncertainty, where the clinician is aware that they do not know. And because of that, you should take the label with a pinch of salt. So maybe you shouldn't take as much importance to that label. So with all of this in mind, we have a setting where ground truth doesn't really exist. There is no such thing as a ground truth. The ground truth is always dirty. And on the other hand, even if it does exist, we have this other amount, which is a degree of uncertainty, that needs to be conveyed jointly with the diagnostics, because we want in the end to have a prediction which is both accurate and safe. And safety obviously is quite paramount in a medical setting. So if I was to say you have a certain condition, full stop, and I'm very certain about it, then if I was to treat you in a very specific way, that treatment, if not ideal, it might cause you some harm. So the ability to convey how certain I am about the disease that you have might cause two things to happen. Either more investigations, so if I'm uncertain that you have a certain condition, it might result in me requiring or requesting more investigations, or it might also result in me providing a type of care which is less dangerous, but maybe also less effective, because I'm uncertain if that's actually the pathology that you have. So conveying uncertainty is incredibly important in the medical field. There's many other areas that are non-medical where uncertainty is really important. For example, if you think about self-driving cars, they are in a similar but slightly different situation. So they're in a similar situation in the sense that even as a driver, there are certain situations on the road where you're not exactly sure what you should be doing. For example, if there's an accident just in front of you, you might not have enough practice to know exactly how you should control the car in the optimal way, so that you drive yourself to safety and you don't hit anyone else, right? And that is, you still take an action, you still decide to do something, but you are less certain about the action you're taking. It's the same thing again in a medical setting. You still need to take an action many times, you still need to treat the patient, but you are less uncertain about what the action should be, and because you're less uncertain, you need to be able to convey that to the controller, the person providing the treatment. The big difference between healthcare and self-driving cars is that self-driving cars often do not have the human in the loop. What I mean by this is that the human itself that is controlling the car, if you're in a fully autonomous self-driving car, you cannot immediately call the human to bring the car to safety, because many times the human might not be paying attention. Obviously, this is if we're talking about fully autonomous cars. While in a medical setting, if an algorithm is uncertain, you can request the human to come back and to look into the data, into everything that is available, and make the decisions themselves. So you can make algorithms safe by the algorithm calling for human help when it believes that it's doing something that is uncertain. And lastly, obviously, uncertainty can have quite a significant amount of financial implications. If you're looking to, for example, stock market prediction, being uncertain of what's going to happen in the future might mean that, for example, you do not want to have a stake in the market because you do not know if, for example, a share is going to go up or down. But in a medical setting, uncertainty can also have a big impact on the financials. For example, the way you manage an hospital, the way you decide to treat or not to treat the patient, and also try to understand what types of treatments could you provide that will maximize the benefit? And I'm not only talking about financial benefit, I'm talking about all types of benefit to both the patient and the healthcare system. So we want to be able to treat the patient in the most valuable and most efficient way possible, and in the way that they will obtain the best outcome given the resources we've used in that patient, primarily when you're looking at socialized healthcare systems. So just to conclude a little bit this introduction, we want to build models to make predictions. But one thing that is incredibly important that we ask ourselves is, can we trust those predictions? How can we sure if those predictions are correct or incorrect? That's normally what we're optimizing for. But how can we also know at the same time how much the algorithm believes those predictions are certain or uncertain? For example, I could say, I think this picture is of a dog, but I'm very uncertain about it. And then obviously you can then explore, why is the algorithm uncertain? You can also say, I know this is a dog and I'm very certain about it. The label is exactly the same. The prediction might be the same, but the uncertainty of that prediction can be very different. So you can think about an uncertainty as some sort of error bars on predictions. How much would you expect the true prediction to be, given all the variations that might exist in both how the model perceives the data, but also how the data itself, the appearance of the data, the amount of noise in the data might change that prediction. And lastly, there's another source of uncertainty, which comes from the fact that the prediction itself might not be fully predictable, right? So you might not have enough information to make the prediction. All of these different sources of error can contribute to an uncertain prediction, and they accumulate. And that uncertainty of the prediction is incredibly hard to be conveyed to someone that is going to be making use of this technology. There's many areas where machine learning depends on good estimation of uncertainty. Not good estimation of the prediction. For that, pretty much all areas would depend on it. But areas where you depend on the uncertainty are things like, for example, forecasting or decision making. For example, if you want to make a decision, you need to understand how much does the model know about that specific situation, or how much is used just providing as a guess, for example. Also, in situations where you have very limited, noisy, or missing data, in those settings, in a data-deprived setting, uncertainty is going to be higher, and you need to understand which parts of the data domain are informed by the training data, and which ones are extrapolations of your model. You also need to have an idea of uncertainty, for example, if you're trying to do modeling or discovery or experimental design, because obviously uncertainty means that your the information that you're extracting from the system is less accurate, and because it's less accurate, if you were to, for example, run a clinical trial, you would require more subjects to be able to conclude that, for example, a treatment is working or not working, because each measurement you're making, it has a larger error bar. So the power that you would need is going to be lower, and the data set size or the population size that you need will end up being higher. So where does the term uncertainty comes from? Normally, when you're optimizing for some machine learning objective, what you want to do is you want to minimize the expected loss. And there's actually two components of uncertainty in the data, and they come naturally from this expectation that we're estimating every single one of these times. So there is a component of the uncertainty which is called the aleatoric uncertainty, which comes from the data itself. That's X, that's our inputs. So our inputs, for example, if you take a picture of a road, or if you take many pictures of a road with cars driving in it, even if you take several realizations of the same picture with the cars and all the objects in the same position, every time you take a different picture, there's going to be slightly different variations in noise. Maybe the sun is glaring in the background, maybe there's shades. So it can be exactly the same scene, but the realization, that exact sample of that scene also contributes to the uncertainty. This is obviously increasingly true in the medical setting. For example, if you're looking into modalities where the amount of noise might be quite high, the presence of noise and that explicit realization of noise, what the noise looks like for that particular image, is going to change your prediction. The position of the object might change the prediction. If you rotate someone's head or torso while imaging might change the prediction. Everything that has to do with the exact realization of that specific sample comes under this umbrella term called aleatoric uncertainty, the uncertainty in the data itself. The second type of uncertainty comes from the model. So the model is what's going to map the input X into the output domain of Y, and that output domain could be anything. Could be a label, could be a category, could be a segmentation, for example. And the model will have some imperfections. The model will never perfectly map input to output. And that can be due to many things. It could just be the fact that the model is not an infinitely supported, or you don't have an infinite number of parameters in your model. Or you can't really optimize a model to the degree that you would like to, because the best tools for optimization that we have are things like gradient descent. Or you might also have models which are just not ideal for the problem you're trying to solve. And because of that, the models themselves will have some limitations. So all the limitations that have to do with how we learn and how the models learn, they come under this umbrella, the uncertainty of the model, also called as the epistemic uncertainty. So what you'd expect is that the uncertainty that comes from the model to be dependent on the model parameters themselves. So as the model parameters grow, and as you have better and better training algorithms, the epistemic uncertainty, then the uncertainty of the model can change and will be reduced. But also when the types of models that you use have better inductive biases, for example, if you're using convolutions in a segmentation setting, that tends to have lower uncertainty than if you use other types of models, because convolutions are good inductive biases to have in a segmentation setting. So appropriate models end up resulting in better epistemic uncertainties. You can also have the same equation now here expressed in a probabilistic setting where you're trying to calculate the log likelihood of the observations. And you see that the log likelihood, that P of Y given X and theta, the given part means is dependent on X and theta. So the ability to calculate the probability of Y is conditioned on the input and the model parameters. That immediately tells you that the prediction uncertainty, your ability to predict Y, is going to be dependent on X and theta, right? So that kind of gives you immediately the idea that that's the source of uncertainty. If X and theta contain no uncertainty whatsoever, so if there's no uncertainty in either the data or the model, then the ability to predict Y is going to be perfect. This means the uncertainty will be low, right? So everything comes from those two sources of uncertainty, at least. So one thing that becomes very important when we are discussing these kinds of things is that we need to really understand what neural networks are. So neural networks, even though they're called neural networks, they're not really neural systems per se, right? They try to emulate some characteristics of neurons, but they're not really how the brain works. What they are is just a series of parameterized functions. So functions that contain parameters which can be optimized, and these parameterized functions are used to model predictions from inputs and the optimized model parameters. So these model parameters are the weights of the neural network, and the feed-forward neural network that we are normally using contain this probability of Y, probability of the prediction, given the input data and the model parameters, or the weights of the neural network. And normally, the probability of Y given X and theta are a nonlinear function of X and theta. So because they go through a series of dense activation functions, convolutional operators, and all of these things. And every time we apply certain types of functions, for example, activation functions are the easiest example, we are introducing nonlinearities in the mapping between X, theta, and Y. And if you think about it, what we're actually doing is we're learning a function that maps inputs X to the output space of Y, given some optimized parameters theta, right? And when we do a forward pass for all parameters theta, and we give it X to the network, a prediction comes out, a prediction Y comes out. And if you think about it, that prediction is a realization of the prediction given that specific instance of the model parameters. So if you were to give a slightly different variation of X, Y would be different. If you were to give a slightly different variation of theta, Y would also be different. So if you were to perturb either x or theta by sampling from those, and obviously we don't have a good way to sample from those at the moment, we would then have many different realizations of what y could be. And if all of those realizations of what y could be were all the same, regardless of how much we shifted x and theta, then you would know that y is a very accurate prediction and a very certain prediction. If every time you sample a slightly different image or a slightly different set of parameters, the value of y changes dramatically, it means that y is very uncertain, right? So what we're obtaining is samples from the true distribution. In a maximum likelihood estimate setting, every time we do this forward pass, we're getting a point estimate of a neural network. So if you think about parameters as being a specific realization of parameters, every time you do a forward pass, you get a point estimate, one specific estimate of a single point over a distribution. So it assumes that the state world is realized by the single set of parameters. So there's a single set of parameters which are fixed. And we also assume that the samples, or the observations, are independent. So with those two things assumed, so that the parameters are fixed and the samples are independent, every time we do a forward pass, we estimate the point estimate of the neural networks. And we use this point estimate to minimize the loss, in this case by maximizing the log likelihood, right? So they're kind of the same thing. So we're using neural networks and we're using point estimates of these neural networks as a way to optimize the parameters of a network itself. This basically results in a series of limitations. Is the fact that neural networks, and by subsequent deep learning systems, have quite an amazing performance on many benchmark tasks, but because we're always calculating these point sample estimates, they tend to be uninterpretable black boxes. We don't really understand well what the parameters mean, and every time they make a prediction, because we do not know what the parameters mean, and we are only estimating point samples rather than uncertainty or distributions of predictions, it becomes very hard to understand if what the network is doing is correct, is incorrect, or if it is incorrect, why is it incorrect? It's also hard to perform reasoning with these networks because they're not really learning causal pathways. They're just projecting input images or input data into output space. You also assume that there is a single parameter which generates the data distribution, right? So this is something that is a big assumption of neural networks, and they tend to be prone to overfitting. What I mean here is obviously there's many techniques to control for overfitting, but for example, if you are in a setting where you're learning about cats and dogs, for example, but you do not have, you only have a very small subset of breeds of cats and breeds of dogs, you might be in a situation where the amounts of dogs and the amounts of cats that you have in your pictures might actually be quite large, but because the breeds of cats and dogs are restricted, if I show your algorithm a type of breed of dog that is very different from everything that you've seen before, the algorithm can still get confused. So overfitting might mean just fitting the data you have, even though it's a lot of it, and not really solving the problem that you have at hand. And it's very hard to know how much can the network generalize to, for example, unseen dog or cat breeds. Same thing happens with diseases, obviously. Lastly, networks tend to be overly confident about their predictions when given an input. And that's because the P of y given x theta is not the confidence. Obviously, probability is not confidence. For example, if you are trying to explain to someone what probability is, there is a very formal definition of what probability is, right? If you are to sample from it, if you have 80% probability, if you are to sample from it 10 times, then 8 out of those 10 times should come up as true, or as part of the prediction would be true. That doesn't mean that that is the same thing as a confidence. So you can say that there is a high probability for this being, for example, Alzheimer's disease, but at the same time you can say, oh, but my data is really poor, so my estimate of that probability might be really bad, so the probability can actually go from only 0.2 to 1, and I'm not really sure what the true probability is. So the two things might sound the same, but they're actually quite different. Neural networks can also be fooled, and this is a type of work which I think is primarily of theoretical relevance than practical relevance. What this means here is that neural networks learn certain patterns, and they learn to project those patterns into some high-dimensional space, which is the feature space, and then go from that feature space back into the logits and then into the probabilities of your prediction. And because these patterns are very, very high dimensional and they're very, very nonlinear, the manifold or the space of projections can actually have a couple of instabilities, which means that if you were to change only a few pixels of the intensity of the images, for example, if you have an image of a cat, if you were to change only a few pixels here and there of the image in a way that a human would still perceive the image completely as a cat, an algorithm might suddenly confuse it as a completely different type of object. For example, by changing a few pixels in, for example, in a flagpole, you can make a neural network believe that that flagpole is actually a Labrador, a dog, right? And that's really interesting, is the idea that because the system is continuous, because we have a continuous function mapping the input x to the output y, we can learn what perturbations in x would have changed the prediction y. So we can change those perturbations in x by changing the intensities of a couple of pixels in the least amount possible to change the label to some other class. And if you have a specific constraint on how do you change those pixels in x, you can then have an image which has very, very little visible changes, but where the output label class is completely wrong, right? This means that our networks are brittle. It means that they don't actually learn to see the world in the same way that we do, and they have weirdnesses in the way that they map inputs to outputs that makes them break under certain scenarios. Obviously, all of these are hypothetical because you need to change those pixels in a very precise way to result in that kind of shift. And those changes are very, very unlikely in real-world data. But it does mean that the model does not really generalize well. A model that has very strong generalizability tends to be much harder to attack from the point of view of changing these pixel intensities than the model that, for example, might be overfit to the data that you're observing. So these two types of uncertainty that I was describing before, this epistemic uncertainty and aleatoric uncertainty, are kind of what is currently seen as two of the easiest, but at the same time better formally defined ways to measure uncertainty. They are simplistic, don't get me wrong, but at least they're easy to explain, and they give you the insight that there's actually many different types of uncertainty that you need to look into, and they have different sources, and the sources of those uncertainties can actually carry quite a lot of weight in terms of your ability to be able to suppress them or improve them. So epistemic uncertainty, as we were describing before, measures what your model does not know. So if your model does not know something, it might be for multiple reasons. It might be that the model itself is not really good enough, but that is a technical issue. You can always improve your model or make your model bigger if you have more memory. But the other part is normally model uncertainty, what your model does not know, comes from the fact that you do not have enough data to be able to tell you what the projection from x to y should be. So there's an amount of knowledge that you need to have, an amount of samples that you need to have, and obviously this is different for every problem, that allows you to make predictions in a way that is confident. If I was to say, can you diagnose patients with some sort of liver condition, given these variables, you need to see enough examples and enough edge cases so that when I give you a new example, you would be able to say, yes, I've seen this pattern before, I've seen a similar pattern before, and because of that, I'm not really extrapolating. I'm just remembering, or I'm just making some logical deduction from what I've seen before to try to give you the diagnosis of these patients. So more data tends to make the epistemic uncertainty, what the model doesn't know, go to zero and minimized. On the other side, the aleatoric uncertainty measures what you cannot understand from the data itself. So these are problems that are intrinsic to the data. Things like noise, things like the way you capture it. So something that where you are claiming that the system itself if it was given perfect data, could make much better predictions. But because the data has problems, you cannot really understand certain things from the data. The sensing is not good enough. For example, your imaging sensor might not be accurate enough and might result in too much noise. There is a certain component of uncertainty that comes from that. And aleatoric uncertainty cannot be explained with more data. It can only be explained, or it can only be improved, by improving the quality of the sensing itself. So the quality of the information that you're feeding into the model. An example of this might be, for example, let's say that you're trying to measure the risk of someone developing some cardiac condition, and you have many variables, including the subject's age and sex, maybe their height, their BMI, and things like this. The accuracy of the measurements obviously are very important. If I was to give you the BMI, for example, without the decimal point, I would only say this person's BMI is 19 or 20 or 21. Those differences are quite substantial in terms of the BMI metric. So you might require more precision in terms of estimating a BMI to be able to calculate, for example, the risk of developing some cardiac condition. So the precision of measurements, or the accuracy of measurements, obviously for in this case BMI, this might sound like a bit of a silly example, because obviously you can get BMI with more precision than that. But if you are in the same setting, for example, if you're acquiring an image and you're trying to predict if someone has a certain diagnosis from an image, the specific realization of noise from that image becomes very important. So the image might be noisier, the image might be occluded, the image might have an artifact. All of those physical issues of how the data is acquired can result in the algorithm becoming very uncertain. So if you think about uncertainty, the uncertainty normally bifurcates into these two, aleatoric and epistemic. So epistemic uncertainty, as I was saying, have to do with the model itself, while the aleatoric uncertainty has to do with the data. And because it has to do with the data, there are two subtypes of aleatoric uncertainty. One of them called homoscedastic and the other one called heteroscedastic. So these are just fancy words to say that one of them has a constant or assumes constant variation of the uncertainty throughout the image. So that's the homoscedastic. While heteroscedastic says the uncertainty or the problems with the data are spatially varying. For example, let's say that your image has a movement artifact in a very specific part of the image. You could say that the quality or the aleatoric uncertainty should be very low everywhere except in the region where you see this artifact. That would mean that the uncertainty, the aleatoric uncertainty that comes from the imaging data, has to be heteroscedastic, because different parts of the image have different amounts of uncertainty. Homoscedastic is just something that says there is an intrinsic amount of uncertainty coming from the full image. Obviously, heteroscedastic is a superset of homoscedasticity. So homoscedastic uncertainty is something where the uncertainty is the same throughout the image. And if you assume that the uncertainty can be different everywhere, which is what heteroscedastic assumes, then they can also be the same everywhere, which means homoscedastic is part of heteroscedastic. But homoscedastic, because it's general and happens to the same amount everywhere, is also much easier to estimate, because you only need to get a single value describing the uncertainty at different locations in the image. So a single value saying that this is uncertainty everywhere, while for heteroscedastic methods, you need to have an uncertainty estimate per pixel of an image, or per feature column that you're feeding into a machine learning algorithm. So when we're looking into the aleatoric uncertainty, we're looking into uncertainty in the data, which you can think about that as noise. Obviously, it's not just noise in the way that we think about when we think about Gaussian noise, for example. It's any type of variations in the data that are not helpful, if that can make sense. So aleatoric comes from the Latin word aleator, which comes from dice players. And that's because it has to do with the randomness of the observation itself. And as I was saying before, homoscedasticity is uncertainty is the same for all inputs, while heteroscedasticity, each observation or each input can have a different value of uncertainty. Note that input here can mean a pixel of an image, But it can also mean different subjects have different amounts of uncertainty. For example, it might be that you're able to measure something really well in a patient because the patient is cooperating, for example, it doesn't move in the scanner, while another patient might be moving a lot, and that means that other patient might have a much larger uncertainty. Every time that we're assuming that inputs have different uncertainty, we are in the heteroscedastic world. Every time we are assuming that all inputs have the same amount of uncertainty, we're in the homoscedastic world. And the other part of the uncertainty, the epistemic one, is the fact that we do not know the correct model to generate the data. This means that the model has uncertainty in the model itself, the types of layers or the types of functions you use to model the inputs to outputs, the parameters of the models, and how much it has converged, and your ability to actually train the model. So model uncertainty has to do with this reproducibility of the prediction. So this uncertainty in the model and the reproducibility of those predictions is dependent on the availability of data. And the more data you feed into the model, the more information the model has to make predictions, which means if you feed more data, the model has more support, and because it has more support, you can then make a better decision. So for example, in this image here below, what you can see is if you were, for example, trying to fit a line into the system, if you were only giving it 1 point, any of these lines here would be viable lines, right? So you could say, oh, the model is like this, or the model is like that, or the model is like this. All of these are viable lines that pass through 1 point. Obviously, this model has a lot of uncertainty. All of these lines are very different. If I was now going to give you, in this case, these 7 points. So if I give you these 7 points here, you'll see that if you trace a line through these 7 points, there's only one line, or there could be small variations of this line, but clearly these other lines that we had before are not viable line fits for these points. You can see here that by giving more data to the model, more data points to the model, we went from a situation where any line is possible to only a small subset of lines being possible. So we have reduced the uncertainty that comes from the model itself. The classic paper that has proposed this was actually applied, come from Jern Gall in Cambridge and Alex Kendall, and they applied this to, for example, as a very easy demonstrator, because everyone can understand this example. They applied this to self-driving cars. So you see here, epistemic uncertainty comes from the model not knowing, and aleatoric uncertainty comes from the sensing uncertainty. So for example, if you have this image here, and you're trying to segment the scene, this is the ground truth segmentation, and this is what the algorithm believes is the correct segmentation. And you see that there are some errors, for example, here and over there, there's errors throughout. If you now look into the epistemic and aleatoric uncertainty, you see something that is very interesting. So first part, the aleatoric uncertainty is primarily around edges. What I mean by this, so aleatoric uncertainty comes from sensing, comes from the image itself. So obviously, if the image was of higher resolution, was sharper, was less noisy, it will allow you to label things better around boundaries. So if you're in the middle of, let's say, the sky, the model can say, this is sky, I can see it is sky, so that's not an issue. But as soon as I get to the boundary of sky, I start being uncertain if I'm now looking into the sky here, or for example, into the trees. So this area has a lot of data uncertainty, sensing uncertainty. My ability to perceive if this is a tree or if this is a sky is the part that is contributing to my uncertainty here. So things around edges, for example, when you're very far away because you don't have the resolution to perceive things, or every time you do not know if a pixel belongs to one structure or another structure, in this case, for example, the road or the pavement. You're not really sure on which one you're in, and because of that, the uncertainty is high in the separation between these two. Conversely, the epistemic uncertainty, as we saw, is about the model's ability to predict things that is not related to the input image, but related to the model itself. So it's about knowledge that the model has learned already. So the areas where you see large epistemic uncertainty are areas where the model gets a bit confused and basically says, I've never seen this before. So for example, it's not very good at modeling the shadows underneath the cars, probably has not seen enough shadows to be able to correctly label these as either being part of the car or being part of the floor. You also see that, for example, in this specific image here, the amount of pavement that we're seeing and the fact there is no cars on the side of the road or trees has caused them all to say, actually, I'm not entirely sure. I've never seen enough examples of pavement and roads to be able to be certain if this is either a road, part of the road, or part of the pavement. So you see that they tend to be blobbier and they tend to be around big areas that the model has not seen enough of before, for example. If you're looking to homoscedastic uncertainty assumes that the uncertainty is constant for different input values. So here, for example, if you think that you're trying to fit a function to the dots here in black, so the dots in black obviously are the observations. If we assume that every single one of these dots here in black have a certain degree of uncertainty, and the uncertainty is the same everywhere, you would fit a function that would, for example, look like this. So you're saying all points have the same error bar. So you imagine that if every one of the black points had a certain error bar that says the true function should be somewhere within this error bar of the black point. So if you had an error bar around each one of the black points, so this black point has an error bar maybe from here to here, and the same thing in this one, you might have an error bar all the way from here to here, and you're trying to fit the function will have to have this strange shape, because the error bar here says the function needs to be somewhere in this region, while that dot there says the error bar needs to be somewhere in that region, and that one says, oh, it should be now part of that region again. So the function needs to fit all of these points, and then it needs to go down and up and down and up, because we are assuming that the amount of noise that these observations have is constant. So both these ones and these ones have the same amount of noise. So the function needs to wobble around to be close enough to all of the points at the same time. Another way to look at the problem is to look into it as a heteroscedastic uncertainty problem. So in an heteroscedastic setting, what we have is, again, the same points going down and up and down and up. But because we are assuming now that different points might have different degree of noise, the error bar of the points here might be very small, while the error bar of the points here might be very large. So the model that you learn could look something like this. It says in this region here, the function looks very smooth because all the points kind of point in the same direction. It makes sense that all the points have a small amount of variance because there's not a single point, for example, up here or down there. So that means the variance in this region of the function appears to be small. While when you get to this other part of the function, the points are so far apart that rather than having a function going up and down, which might not be biologically very, very plausible or physically very plausible, you could just say my model is very uncertain. So it says the function could be somewhere over here, but that's because these points here probably have measurement issues. So they have a type of aleatoric heteroscedastic uncertainty, which is very high in this region here, but actually quite low in that region there. So he has the kind of behavior that we would expect, where you have a lot of points and all the points point in the same direction, then the uncertainty is small. And when the points have very significant discrepancies between them, rather than fitting them, we can just say, actually, the model appears to be very uncertain in this part of the data. One way to model uncertainty is with something called Gaussian processes. Obviously, Gaussian processes are named after Johann Carl Friedrich Gauss, who's one of the great mathematicians of our world, and the one that was given the name of the normal distribution because of all the studies he has made in that domain. Gaussian processes are the idea of trying to model variances and covariances between observations using Gaussian distributions. If you imagine that you have a feature which only has two dimensions, let's just say you have someone's age and BMI, for example. You just have two features. Age could be x1 and BMI could be x2. So each one of these points at that location 0, or each one of these points here in gray, is going to be a combination of age and BMI. In this case, all these points are d-means and have a variance of 1. So we normalize the points so that they end up having a mean and a variance of 1. And we put them in this specific space here, where again, different x's, so x1 will have the age and x2 will have the BMI, and the mean is going to be 0, 0, and the variance is going to be an isotropic diagonal Gaussian. So if this is the situation, right, what we're basically seeing is that there is no correlation between x1 and x2. So the age, for example, might be uncorrelated from BMI. If in another situation, age might be actually correlated from with BMI, you'll be like here, for example, someone that is younger would, in average, have a slightly lower BMI, while someone that is older might, in average, have a higher BMI. Again, this is all hypothetical. This is not data from BMI, it's just to give you an example. And what you see is, if I was to ask you, for a person of a specific age here, for example, if you now look at the plot at the left, for a person of a specific age, what would be their expected BMI? So we need to take samples along this vertical line, right? We need to say, oh, for this age, the BMI should be either down here or it should be up there. So there's a large variance in BMI for people with that specific age, x1. While if there's correlation between the two, if you know someone's age, x1, you know that that person's BMI is somewhere here. So this is called marginalization. If you were to say, what is the probability of someone having a specific BMI, given that I know their age, x1, you know that for this distribution, the expected BMI will be somewhere in this range, which is small, while for this one here, the expected BMI will be a much larger range because you have less correlation. So the relationships between x1 and x2 are modeled here by this covariance matrix, which we can find between the data. And if you then take specific axes along that this Gaussian distribution, you are marginalizing the distribution according to certain variables, and that allows you to then access the probability distribution of other variables. This is something that you'll see later on that is quite useful. So when you're marginalizing the probability of a variable, so when you're calculating something like this, you're calculating p of x2 given that x1 is equal to a certain value, in this case small x1. You can also rewrite this like this, so p of x2 given x1. What we're doing is basically we're taking that Gaussian distribution and we're finding the probability distribution along a specific axis x1, so that you get basically that distribution that you're expecting. And this distribution here, because everything is modeled as a Gaussian, is also a Gaussian. So you can calculate p of x2 being a Gaussian and being a function of x1 if you were to know x1. The interesting thing about this example that I was giving before is that it can be used for many other areas. For example, let's say you're now wanting to model a time series. So let's say x1, x2, and x3 are 3 time points of something that is happening, let's say a blood measurement of some sort. And f1, f2, and f3 are the values of that blood measurement. So this is now a time series, right? There's something happening in time, and we want to understand what the time series is. You could say, oh, this is a line, but we do not actually know if the function here should be a line. It looks like a line, but it could have many other forms, right? And this becomes now a problem of what is the optimal function that we should fit to these points to create a time series. One way that you can feed this into a Gaussian process is to use something called a kernel. So in the kernelized setting, what you can do is you can calculate this kernel. So kernel is nothing more than a specific equation that you're going to apply to your data, which is going to calculate relationships between points that you've observed. So for example, if you were to apply this kernel equation here, this e to the power of minus xi of the norm of xi minus xj squared, so the L2 norm of that, what you're going to basically be doing is calculate the kernelized function of the input data. So if you were to feed these values here into this equation there, and you calculate it for each version of I and j, so for each xi and each xj, you're going to end up with a kernel matrix that's going to look like this. And this kernel matrix is going to naturally have a mean of 0, and this is going to be the kernel covariance function, let's call it. So this function here tells you the relationships between this point and that point and that point. And these relationships are a function of a few things, primarily the distance between the points. So this tells you that, for example, the relationship of point 1 with point 1 is 1. The relationship between point 1 and point 2 is 0.7. And the relationship between point 1 and point 3 is 0.2. And that's because it's further away. So the influence that point 3 should have on your ability to fit the function in point 1 is dependent on the distance between them. And again, you see that, for example, for point 2, the relationship with itself is now 1, and the relationship with the point before, in this case x1, is 0.7, and with point 3 is 0.6. And that's because this point is closer to the one after that, and also closer to the one before. So the distance to x1 and x3 is not that small for either of them. And you see the opposite happens here. The other part that you see is that this matrix here is diagonal, right? Sorry, not diagonal. This matrix here is symmetrical. So you see that on the upper diagonal and the lower diagonal side of this matrix is symmetrical. So the way you can think about this is that in between these points, if you were to marginalize the distribution to be able to know what the function should be at some point between, for example, x1 and x2, what you can use is you can use the same thing as we did before. So this assumption that there is this multivariate Gaussian kernel linking the points x1, x2, and x3. And you can marginalize the Gaussian and calculate the distribution of the marginal. So you say, what if my point is somewhere between x1 and x2? So is at this specific location here. So if you were to marginalize in that specific location, you're going to end up with a distribution of the kernel that you've seen before, basically saying that the function should be anywhere between this point and this point with this mean and this variance. So it gives you a way for you to know the mean and the variance of points in between points. And it will say again that the variance here should be like this, the mean and variance should be like that. So if you were to fit functions, it will look something like this. So this basically tells you that the functions that fit these 3 points are any function that will be between these two blue or purple lines that you see here on the screen. And obviously, because this is a Gaussian distribution, actually is not between these two lines, but these two lines represent the 95% confidence interval of what the function should look like. You can also see that the linear function is probably part of this, right? So if you were to trace a linear function here, it will probably go roughly through the 3 points, and it will be between these bounds. So Gaussian processes give you a very formal way for you to describe all possible functions with a specific type of Gaussian kernel and length scale that will pass through all of these points, and also give you an ability to interpolate between any of these with error bars that are appropriately scaled by the model that you've chosen, by this Gaussian model that you've chosen to the data. Obviously, these models are dependent on certain hyperparameters, like the length scale of the model, but even those can be integrated out. So you can actually have a very formalized way of calculating all possible functions and relationships between points of data. So Gaussian processes are a generalization of the multivariate Gaussian distribution for infinitely many variables, and they are Bayesian non-parametric. So the number of parameters grow with the size of the data set. So if you have 1,000,000 points, you will have 1,000,000 parameters, because the kernel matrix will need to know the relationships between all of those points and all the other points. So it's non-parametric because you basically end up with more parameters than data. So it is still parametric because it's Gaussian, but it's non-parametric because you're not restricting the classes of functions to the amount of data that you have. So GPs are distributions over functions, and they're not point estimates. And they can be seen as the Bayesian versions of many of the most popular algorithms, for example, like SVMs. And similarly to SVMs, they also use kernels. Most of the times, kernels tend to be that kernel you've seen before, but there's actually many other kernels and constraints on kernels and priors on kernels that can be used to model things as Gaussian processes. And what I mean by kernels here is, if you remember from a previous lectures back, if you were to transform that data that you see here on the left, which has 2 dimensions, the x and y dimension, where you have 2 classes, the triangles and the dots being in 2 concentric circles, if you were to apply, for example, a kernel that calculates the Gaussian proximity between them, for example, and map that data into a 3-dimensional space, you'll end up with the data on the right. And you see that the data on the right is very easily separable in the z direction, while the data was not separable with the plane when it was in 2 dimensions. So kernels allow you to project data from a lower dimensional space to a higher dimensional space that preserves certain types of relationships in the data. And these relationships can then be used to better model the data and to understand the relationships better than you could before. So GPs, as I was saying before, are distributions over functions, and they are fully specified by the mean and the covariance matrix. That's everything you need to know for you to describe the GP, because the GP is nothing more than that covariance operator telling you the relationship between the different points using a specific type of kernel. Obviously, the problem is the size of the covariance matrix can be quite large if you have too many points. So GPs are theoretically incredibly nice, and they are actually being used in many, many scenarios, but they tend to be hard to be used in situations where the number of data points is really large, because the size of that covariance matrix will explode. So if you were to use GPs for regression, and if I was to give you a data set that looked like this, if you were to feed GPs, it would be easy for me to argue that, for example, all of the following functions will be something that we could use. So this is a slightly shrunk version of the previous one, and what you basically see is you see that the range of the plot has changed slightly. But what you see is that where the points exist, where data exists, all of the functions kind of agree that that should be the right place for the functions to be. For example, in this area here, you see that the uncertainty of the functions that we can sample from this Gaussian distribution, they're all very tight. But as soon as we go outside of the area where data exists, then the model is saying any of these could be a viable solution. So it's telling you that as soon as you go out of your area where your data exists, of your interpolation area, and you start extrapolating, the model uncertainty should increase dramatically to the point where any function becomes possible. And the further out you are, obviously, the bigger the uncertainty would be. The types of kernels that you use, or covariance functions that you use, assume different things from the data. For example, if you're using the squared exponential kernel, the squared exponential kernel assumes that points have a local covariance. So a point in a specific location x is going to influence the points around it, but the point here, for example, will not influence the point in a location that is very far away. So the distance between x and x prime, according to a specific length scale, so the length scale is some parameter that you choose that tells you how far away that influence goes, is going to go down very quickly, right? So the amount of relationship, or the amount of influence that the point has on these neighbors, is going to go down very quickly as we go out with distance. And if you look at the covariance function itself, this is the structure that you're kind of imposing on the structure. So things that are in a specific location are going to influence the things that are just immediately next to them, but not something that is very far away. Other kernels, for example, the exponential kernel, that look like the previous one, assume that the kernel function looks like this, again with another length scale. But because here we don't have the x squared, or we don't have the x minus x prime squared, the function is going to go down much, much quicker, and is also going to have a much smaller influence. That means that the spatial relationships between points is going to be less constrained. Obviously, if the length scale is large, you can still increase the constraint, but it's going to be sharper, and that allows for more high-frequency functions to be created. So while in the previous slide, all the functions that you sample from will be relatively smooth because of the x squared term and the length scale, in the exponential kernel functions, they tend to be slightly sharper and more jagged than before. So we're prescribing a different family of functions to fit our data. If you were to use, for example, the Mattern 5.2 kernel, which again is similar to all the other kernels that you've seen before, you now see that the types of functions that you're modeling are according to this equation here. And this equation here now has the square root term there. Again, it has an x minus x prime squared, but it has a square root term both here and there, which means that you end up with these types of functions which are still smooth, but they have some other slightly different patterns that allow for slightly sharper variations in frequency than you could before. Lastly, and again, there's many kernels that you could use, but this is to just show you that you could use pretty much any kernel you would like. You could also use a cosine kernel. So cosine kernel says that the relationships between points are dependent on the cosine of that distance between them. So a point in a specific location is going to depend on its neighbors immediately, and then not depend on them at all, and then depend on neighbors after that, and then not at all again. So a point in this location here will depend on its immediate neighbors, but it might not depend on points here, and then it might depend again on points there, according to the cosine function. So cosine covariance functions are normally used for models which have periodicity, because obviously cosine functions themselves are periodic. The cosine function obviously is going to be a function of the length scale, and the periodicity is also going to be a function of length scale. So we need to be able to formulate something which will have the correct periodicity so that you can model those relationships correctly. But it's just to show you that the kernel doesn't necessarily have to be something that will be monotonic, starting very high and getting lower and lower as the points are further away from each other. Okay, so if you have the time while watching the lecture, it would be a great time now for you to go through the practical part 0, which is we're trying to implement a little Gaussian process as a way to create a model of what the data looks like. So we're not going to learn Gaussian processes from data. So we're using Gaussian processes as a way to generate data so that we can do the same thing as Gaussian processes do, but using neural networks. So Gaussian processes are going to be used today as data generators, which have an implicit series of functions underneath that we can sample from. And what we will try to do is to recover the same uncertainty, but rather than using Gaussian processes, which as I was describing before can have quite a big burden, computational burden to them, we're going to use neural networks to approximate the same kind of error distribution. When you're training neural networks, as I was saying before, when we're looking into these Gaussian processes have this intrinsic Gaussian representation of the data. And if you think about it, when we're fitting neural networks, we actually have something relatively similar. Let's say you're trying to fit these points here, these little triangles here, and you're trying to fit them with two variables, with the slope and the intercept of a line. And if you think about it, that's kind of what a fully connected layer plus an activation function are trying to do. They're trying to fit lines, and then the nonlinear activation allows you to then model nonlinearities. So you have these two parameters here, and these parameters model the intercept and the slope of this line here that pass through these points. In a non-Bayesian setting, you are basically assuming that the points have point estimates. So you can obtain the true value of the intercept and the true value of the slope of the data. Because you assume that you can obtain these true values, you have one single realization. And you see that the data wobbles slightly around this line, which means you can then have uncertainty coming from the fact that maybe the line should actually be slightly steeper, and maybe these estimates are not the best. The other way to think about the same problem is if you try to, for example, model the problem as a distribution. So you could say, I do not know what the intercept is, but it should have this distribution of values. It should be somewhere along this intercept area. And the slope should have this range of values again. So we're saying if we were to sample anywhere from these intercept locations, let's say we're going to sample there or there or there or there or there, right? If we were to sample at these ones of any of these locations, and then after I sample a specific location of the intercept, I was to then sample a specific slope for that intercept location, in this case one of the red lines, you're going to then take a realization. So you can say I'm going to take a location in the green distribution, and then after I know that location, I'm going to take a sample from the distribution of slopes, which will then give me a line. That is one of the many possible lines that you could take. If you were to take a different sample from the intercept distribution and then a different sample of the slope, you're going to end up with a different fit to the data. So if you were to do this, if you were to obtain these distributions here, you could then get multiple fits to the data, and by sampling from these distributions, you could then know what your function looks like from the point of view of its uncertainty. So what we want is to basically do this. We want to go from a situation where we have your input data x, we're multiplying by a, let's call this a weight matrix, but this, you can think about this as the slope of the previous equation, and add the bias term, which is the equivalent of the intercept of the previous slide, and you want to then make a prediction, z, and then that prediction goes through some activation function, in this case, for example, a tanh, and then this activation function gives it to a different weight matrix, so a different set of slopes, which then adds a certain bias term, which gives you y prime, and then you pass it through a ReLU, and you end up with y, which is your prediction. So this is a mini neural network that has two layers, two fully connected layers, and a tanh activation function between the first and second layer, and a ReLU activation function between the second layer and the output. This is a very, very standard neural network, nothing special. And what you're seeing that is doing is you're basically fitting a plane here, passing the output of that plane through a tanh, and then fitting another line here to that tanh, so that you end up with that prediction, and then putting it through a ReLU so that you end up with an activation which is going to be between 0 and the value of x prime. If each one of these values there, rather than being a scalar value, so if each one of these parameters of the network, rather than being a single parameter, a single scalar value, floating point value, if they are a distribution, then you can still do exactly the same thing. So obviously, if all of these distributions here were Gaussian, then you could say you only need to store two things, the mean value of the Gaussian and the variance of the Gaussian, so the width of the Gaussian. So if each parameter now becomes a mean and a variance parameter, both for the fully connected but also for the bias terms, every time you take an input x and you pass it through one of the many realizations of W1 and B1, you're going to end up with z prime. And for every different realizations of W1 and B1, you're going to end up with a different value of z prime, which means you're going to end up with a distribution of z primes. The distribution of z primes can then be passed through a distribution through the tanh to get the distribution of z's, which you then give to the second layer of the neural network, which is again going to be a distribution that gives you a distribution of y primes. You then pass the distribution of y primes through a ReLU, and you end up with a distribution of y's. So by changing the parameters of networks, the w's and the b's, from scalars to distributions, we end up with predictions which are themselves distributions. So the way to do this, and we're going to implement it today, is actually quite costly, but it can work very well for certain types of problems. So the interesting thing about today's lecture is that we're going to be focusing on one-dimensional problems. So we're going to be looking at single-dimensional problems, or one-dimensional problems, because they are very visually appealing. You can clearly see very well what uncertainty looks like. And you're going to see that for that kind of scale, this kind of approach where parameters are modeled as distributions rather than as scalar values, you can have quite a good performance. So if you were to think now about a network being connected, the distributions, obviously they can be modeled as Gaussians, but they can also be modeled as non-parametric distributions. That is a little bit more complicated, but they can. It's just to say that each one of the weights and bias terms are modeled as distributions. So the network goes from what you see on the left, which is that certain points and bias terms. So the bias terms here are these i's that you see here. These are the bias terms. So the network, rather than having point estimates of all of these parameters and point estimates for the bias terms and then put them through a series of layers, it has distributions which you sample from, and that's it. So in this Bayes by backpropagation type of approach, obviously this Bayesian approach assumes that the data is fixed, and what you want is to update the model beliefs by updating the model parameters. And you can do this exactly in the same way as you did before with gradient descent and with backpropagation. The only difference now is that the parameters, rather than only having a specific scalar value, they now have a mean and a standard deviation. And so the gradients need to be updated for those two parameters at the same time. So if you were to, for example, apply an algorithm like this to the MNIST dataset, if you were to, for example, train with stochastic gradient descent, the algorithm many times gets stuck in some sort of a test error local minima. And if you were to, for example, apply dropout to the data, you can often get out of that local minima because dropout introduces some stochasticity into the model, which allows you to jump out of many local minima, but also you'll see later on that dropout is actually a small approximation of what this Bayes by backprop does. If you were to actually train the Bayes by backprop algorithm, you'll see that the test error actually optimizes slightly slower, so the learning function is going down slightly slower than with dropout, but you do end up with a slightly better result on the MNIST dataset. And this is a figure from that paper that you see down there from Blundell et al. 2015. You also see that the weights of the prediction tend to be wider with Bayes by backprop, and that's because you're properly modeling the uncertainty rather than just trying to model a much smaller set of uncertainties using the other models. So the weights themselves of the matrix tend to be wider because you're assuming that there is a class or a series of functions that are actually modeling the data implicitly. And that normally means that the model is more realistic and is able to generalize better just because we have access to a larger range of parameter weights. It would be great if you could now pause the video and go back to the Jupyter notebook. We're going to be implementing the Bayes by backprop part now. So we're going to be looking to part 1 and part 2. And obviously we're going to go through this through the tutorial session later this week. There are other ways that you can use to model uncertainty. So far we've been looking at Bayes by backpropagation, which is a way for you to change your neural networks. So you need to change the neural network architecture itself to be able to model these things. And they look very nice when you're looking into fully connected layers and activation functions because it's very clean. But as soon as you start applying the same thing to methods that require convolutions, the solution is not as easy as you would expect. So if you were to, for example, try to model uncertainty, one way that you can do is to try to model the aleatoric uncertainty. So the uncertainty that is inherent in the observation noise. Because it's a type of uncertainty that depends on the input data and perturbations and the different realizations of the input data, one thing that we can do is to change the input data itself, because we know how to do that, and see how the model reacts to those perturbations. So for example, if I was to show you all of these different pictures of cats, you would know that all of them are cats. But in reality, they're all exactly the same cat. It's just that these different cats are rotated in different ways. Some of them might be mirrored between the left and the right. Some of them might be slightly zoomed in, but they're all cats. So the neural network should always give the same answer for all of these different cats, but it won't. So most of the times the network will not give you the same exact output for these different images. And the probability for the first, the second, the third, the fourth image to be cats will be slightly different. And the variations in those probabilities will tell you how certain the model is that this is actually a cat. This is called test time data augmentation. The reason that it's called like this is because at test time, when you're doing testing, when you're validating your model and you're doing inference, right, you augment your data by applying rotations, by applying noise, by applying whatever you want to apply, that in a way that perturbs the input data. Obviously, it needs to perturb the input data in a way that doesn't change the labels. For example, if you were to add a dog face on this image, obviously the image would not be a cat anymore. For example, if you're trying to do segmentation, and if you were to rotate the object and moving the object out of the same place, then obviously the segmentation cannot be the same because now the brain or the organ is in a different location. So you need to perturb and augment the data in a way that does not change the label. And by perturbing that, you then end up with a augmented image, which you then feed through the network, and you end up with a slightly different prediction. And that difference in prediction, or the uncertainty of the predictions that come from, for example, the variance that you're observing between those predictions, is giving you what you want in the end. Other ways to calculate modular uncertainty is by using something called ensemble methods. So as you know, neural networks try to minimize this incredibly complex landscape, and they try to do this using stochastic gradient descent. And stochastic gradient descent, the keyword stochastic, the reason that we use stochastic gradient descent and not just gradient descent is not only because we don't have enough GPU memory to fit all of the data in GPU, is also because the stochasticity, the randomness of the gradient descent process, gives you some ability to get out of certain types of local minima. Obviously, we are in a very high-dimensional landscape. In this image here, we're looking into a three-dimensional landscape, but our landscape is much larger than 3 dimensions. And because we are in such a high-dimensional landscape, we will be in a setting where this landscape, where if you were to initialize the training of the model in different locations of this landscape, so for multiple random initializations of a neural network, the optimization might end up in slightly different parts of the landscape. So if you were, for example, to train a neural network many times with a random seed, each time that you train the network is going to give a slightly different network, actually a substantially different network many times. They might have the same performance, but the parameters might be very different. And all of these different networks have solutions at different points of this landscape. So these solutions are actually giving you different optimal, local optima of what the network looks like. If you were to then calculate the ensemble of them, so an ensemble is, for example, the average of those different predictions, each one of these models is going to help each other get a better prediction. So the ensemble prediction tends to be better, but also the differences or the variance between the different predictions that you get from different models give you an uncertainty because they tell you what is the variability that you'd expect from different models. So if a model says this is definitely a cat and the other model says this is a dog, then you know that the two models are disagreeing with each other, which means that the prediction is more uncertain. So you can use the concordance or the discrepancies between these predictions to be able to know if the model is uncertain or not. Another way to do uncertainty estimation is to use something called dropout. So you probably remember dropout from the first few lectures. This is something that disappeared for a while, for a couple of lectures, but now it's coming back. So dropout is a way for you to introduce stochasticity in the network itself, but it's also a way for you to introduce ensembling in the network itself. What do I mean by this? So if you remember dropout is a way for you to mask specific nodes of a neural network by masking it with the dropout mask. And the reason we were doing this before is because we wanted the network to co-adapt the different parameters. So we wanted the network to basically say, do not rely on this parameter or that parameter or any parameter for that matter to be able to make the prediction. Because if this parameter, if you are too reliant on this single parameter, and this parameter is wrong, then the prediction is going to be wrong. So by masking a network with a dropout mask, we are basically forcing the network to create feature representations that are that represent the same thing in different locations, but they're also more resilient. So we are creating a representation that can model the same concept in many different ways. And every time we apply a dropout mask, the model is going to give us a slightly different prediction. So actually, dropout is a way for us to get multiple different predictions from a network. So if you were to apply dropout at test time, so normally dropout is applied at training. What we've seen before is you apply dropout during training, and then when you're doing inference, you turn dropout off, which is where you set for example, the PyTorch flag to eval mode rather than train mode. And when you're turning dropout off, you're kind of saying, oh, everything's connected again, so I'm not going to apply the dropout mask. But here we actually want to have dropout on during test time, during the validation. So if you were to apply dropout during validation, every time you mask with a different dropout mask, you're going to end up with a slightly different prediction at the end. And this prediction and the differences between different predictions are going to give you an idea about the uncertainty of the system. So if you were to forward pass data through this network many times, and every single time you pass the data through this network, you were to apply a different dropout mask. So if you were to delete or to null different nodes of this neural network, you'll end up in a situation where the predictions will be different for every single forward pass, and the variance between those predictions are going to give you a degree of uncertainty of the network. This approach is become very, very popular because it's incredibly simple. You just turn on dropout and you do multiple forward passes at test time. But it does have some caveats. For example, the dropout masking parameter, the Bernoulli probability that you give it, is an hyperparameter, which there are ways using something called concrete distributions, which there's other papers focusing on that allow you to optimize for that all in one go. But it does become dependent on this hyperparameter because the amount of masking you do is going to give you different degrees of uncertainty. And if you do too much masking, obviously you then deplete your network of any capacity to do anything useful. And in his thesis, Yaron Gal, which finished his PhD now 5 years ago and is now a professor, I believe either in Cambridge or Oxford, I don't quite remember. But in these theses, what was shown was that the process we've seen in the previous slide, this dropout process, is equivalent to what normally happens in a Monte Carlo setting. So it was actually named Monte Carlo Dropout. So Monte Carlo is a way for you to perform stochastic forward passes through a network or through some function and average the results using assembling methods. And you can then calculate the uncertainty by basically calculating the variance of that system. And obviously the amount of forward passes that you do needs to be large because you want to get the full distribution, and also is a function of the probability of the units being dropped. So if you have more dropout masks, you normally end up with having more samples required to get a good estimate of both the expectation and the variance of the predictions, which you see over here. So in the Monte Carlo dropout sample, in practice, what you do is you give a point or an image or some data vector x to a neural network, and you're going to apply dropout at test time. So you're going to drop units at test time. You do this n times, and n times is just dependent on how much computational budget you do. The more you do normally, the better, but obviously it's going to take forever. And you look at the mean and the variance of those predictions. This is exactly what I've been saying for a while. So you see the code to do uncertainty estimation is actually really, really, really small. You just have a model, you have an input data x, you have a number of iterations that you want to apply, and you have some options which you might want to use. And what you do is you do a for loop over a certain range, and within this for loop you're going to calculate the mean of those outputs, you're going to calculate the variance of those outputs, and then you're going to pass them through a function, so you end up with a mean and a standard deviation. So this mean and the standard deviation, so the mean is the ensemble of the prediction, and the standard deviation is now the uncertainty of the prediction. And those things is basically what you want to end up with as the final uncertainty estimate of your model. So if you click on the image, primarily if you are in the PDF, because here you can't click on it on the video, it will point you to Yaron Gal's website where he has a couple of demos where you can click points in certain parts of this one-dimensional function and train data interactively so that you see what the model is actually trying to do in the background, which I think is a very, very nifty demonstration. So what do we want to optimize for? So in a deep learning setting, our model is a model that is an f of x in order to predict a variable y, right? So we want to basically learn a function that if given x, it wants to predict y. And if you are in a regression setting, that what you normally do is you apply some sort of L2 norm between y hat and y. And if you are in a classification setting, you apply some function like a softmax cross entropy on y hat, right? Those are what we would normally do in a regression or classification setting. Obviously, loss functions can change. While in a probabilistic deep learning setting, you want your function f to be a function of your input data x, but you want your function to give you two things back. You want your function to give you a mean prediction, which is the y hat, but you also want your function to give you a variance squared, which is the uncertainty of the model. The loss function then becomes a little bit different. So for example, the loss function on the regression setting becomes like the ones you see here, which is y minus y hat squared divided by 2 sigma squared, and then log sigma squared. So what this loss function here does is something that is really interesting. So for example, if you're regressing, what this says is normally you would be penalizing the difference between your prediction and your ground truth, right? This is what you do in a normal deep learning setting. Well, here you're doing the same thing, but you're saying if the variance of a specific point is very large, so if the prediction is very uncertain, then you want to give it less emphasis. So you're basically saying if the model believes a certain point that is not sure of a certain prediction, then you don't want to take that prediction as much into account. And to avoid the situation where the network just makes sigma very large for every point, because obviously if sigma is large, the loss is minimal everywhere, there's this extra constraint here that says that the log of sigma squared also needs to be minimal. So the variance needs to be small over all the points. But if the variance is large in some points, the L2 between the prediction and the ground truth for that point is not going to take as much into account in the loss function. Same thing in the atrophy in the classification setting, where the mean estimate of y is here and the variance estimate is there. And if we sample from the distribution, we're going to end up with a series of samples that we can pass through the softmax cross entropy, which is going to give you a loss. And that basically is going to give you a probabilistic way to optimize for cross entropy.
Okay, so now let's go back then to the Jupyter Notebook and let's try to implement the Monte Carlo dropout, which, as I was describing, is really simple. It's just making sure that dropout is turned on when training your network. And then at inference time, also apply dropouts multiple times. So do not forget to change the train mode to eval mode, or actually to make everything in train mode, both at train and eval, so that every time you apply dropout, the dropout is actually active. And then apply that little algorithm to provide a mean and a variance estimate, or a mean and a standard deviation estimate of what the prediction is. The last way to estimate uncertainty that we're going to study here is using something called deep ensembles. So deep ensembles is similar to something that you've seen before, but basically deep ensembles they're a non-Bayesian way to estimate uncertainty. So the issue with the previous approaches that we've seen so far is that they all rely on a single function or single network to be able to make the predictions. So if, for example, a specific network has a specific type of inductive bias, that means it does not work very well for a specific problem, then that network is going to end up not providing good measurements or good predictions anywhere. But that doesn't mean that the predictions will be different. It might always provide the wrong, but consistently wrong prediction. So in an idealized setting, we would like to have many different types of networks. And by different types of networks, I mean with different types of architectures, with different types of layers, with different types of neural networks that you would use. And you would like to then be able to make predictions with different neural networks, all trained in a similar way. So deep ensembles is the everything in the kitchen sink approach in uncertainty estimation. So you can use everything together. You can have ways to estimate uncertainty via Monte Carlo dropout. You can have ways to estimate uncertainty using Bayes by backprop. And if you now have multiple network architectures, you can ensemble multiple different network architectures and calculate the variance of those. And by doing this, you can then have variances which will be capturing the real data much more often than other networks, because they are not restricted to a subset of functions as defined by a single network architecture. So they are non-Bayesian methods. They generate very high quality uncertainty predictions, even though they are not theoretically very well funded, because they're just a bunch of different neural networks going through the uncertainty process and averaged together. They tend to be with the right degree of confidence when you're out of distribution. So because you have different classes of functions modeling your input to output mapping, when you're out of distribution, when you don't have data to support your predictions, deep ensembles actually have very wide uncertainties, which is what you'd expect. And the models don't actually have to have dropouts. So if you just train different neural networks, vanilla neural networks without any dropouts, but if the neural networks are different, the differences in predictions from different neural networks often give you very good estimates of uncertainty that do not require dropout to be used. So for you to use deep ensembles, you can just use, for example, let's say you're trying to segment an image. You could use a UNet and a VNet and a high-res net and a deep medic. So you use all of these different architectures. You maybe even train these architectures with different number of layers, different depths. You might train them even with different loss functions. So you basically end up with 20, 30 different models that have been trained in a slightly different way. And what you do is every time you now have a new image, you pass this image through these 20 or 30 models, and each one of the models are going to give you a slightly different prediction. And obviously, if you now calculate the average of the prediction and the variance of the predictions, you can then now get the expectation and the variance of the uncertainty of the predictions. And if I'm just showing you pictorially what you'd expect, what you normally end up with something that looks like this. So if the true function is the function in blue, if you were to calculate just with the standard point estimates, you'll end up with a fit that will look like the one in the left. If you apply some form of uncertainty estimation using some other methods, you will end up with the ones in the middle. While if you do an ensemble of 5 models, because the models have quite a lot of variability when you're out of distribution, you'll end up with the image that you see there on the right. You see that, again, when the points exist, you will be in a setting where the models all fit the same thing. But as soon as you go out of the area where you have support, you'll end up with a solution space, which is quite broad, where we don't really know what the function looks like. And you see all of these miss the fact that this function here twists down around here. While for this kind of approach, because the models have a lot of variability, one of the many models will actually have the right answer, so the error bars will be capturing the truth.
I hope you enjoyed today's lecture. Obviously, in a few days' time, we're going to have the part 2 of the same lecture, where we're going to see a substantial amount of applications of uncertainty estimation to medical imaging data, for example. And by the end of this lecture, I hope you now understand that neural networks can indeed model uncertainty and how they can model uncertainty, either via the way you model the parameters of the neural network, or by ensembling, or stochasticity, or test time augmentation. You understand the differences between true Bayesian methods, which are the ones where you're actually modeling the parameter distribution, and the ones that try to approximate it via methods like Monte Carlo Dropout sampling. You are now able to differentiate aleatoric and epistemic uncertainty. So in this case, the uncertainty that comes from the data itself and the uncertainty that the model has intrinsic to itself because of the model itself or because of the amount of data that he has observed. And you can also differentiate between homoscedastic and heteroscedastic models. So the ones that have constant variance and the ones that have non or sample specific variance, which then allows you to be a little bit more flexible. There are a few additional resources that you might want to look into. There's quite a few repositories, both from Yaron Gal and a couple of other contributors, which have really, really nice demos, which you should look at. And it's also an area where is very much of interest to many, many readers throughout, and obviously very relevant to medical imaging and medical data in general. So there are very good blog posts that you should definitely be reading because they explain this to a much more technical detail. And the lecture today has been more on the intuitive side of the equation. And as always, if you have any questions, do not hesitate to ask me. Send me an email or ask via Keats and just post it on the forum of the channel, and we can then go through them. Bye-bye.